Okay. On the last session we had op-amps from Floyd, and we didn't cover our log and anti-log amplifiers. I'll need this tomorrow. Okay, so let's go through. Log and anti-log amplifiers are used in applications that require compression of analog input data, linearization of transducers that have exponential outputs, and analog multiplication and division. Okay, logarithmic amplifiers are used for analog multiplication and division. Okay. They are often used in high-frequency communication systems, including fiber optics, for processing wide dynamic range signals. Yeah, they are used in signal processing too. The logarithm of a number is a power to which the base must be raised to that number. A logarithmic amplifier produces an output that is proportional to logarithm of the input. Okay, it does something like the integrator. The output signal is integrated of input, and same here happens here. Output signal is logarithm of input signal, and the same with anti-logarithmic. Amplifier takes the anti-log or inverse log of input. The key element in log amplifier is a device that exhibits a logarithm characteristics that, when placed in a feedback loop of an op-amp, produces a logarithmic response. Key this means that the output voltage is a function of the logarithm of the input voltage, as expressed by the following general equation. As we said in the beginning, minus k was k, ln v in. K is a constant, its natural logarithm to the base e. Okay. Natural logarithm is an exponent to which the base e must be raised in order to equal given quantity. Okay. The semiconductor P-N junction in the form of either diode or base emitter junction BGT provides a logarithmic characteristic. You may recall that diode has a nonlinear characteristic up to a forward voltage of approximately 0.7 volt. This voltage at diode is opened. The figure shows that the characteristics curve that VF is forward biased current. Yeah, that's right. The diode curve is nonlinear. They are not only in charging current. It is logarithmic, and it is specifically defined by the following formula. EF is ER in power Q. You have to know this formula from introduction to the electronics. This is current of forward biased diode, where ER is a reverse leakage current. Yes, Ln EF is we take Ln from both sides, sum of and we have, when it's logarithm formula, logarithm characteristics, that the multiply means not division but multiplication. Adding to logarithms means multiplication, and that's what used here, right here in this part. Okay. The difference of two in terms equals ln of the quotient of terms. Okay, and this is the last formula. When you place a diode in the feedback loop of an op-amp circuit, as shown in 1433 and 1430, it's right here. When you place diode in the feedback loop of op-amp circuit, as shown in here, you have a basic log amplifier. Okay. In the integrator, we had in the feedback loop capacitor. In derivation, we have got resistor, and in logarithmic amplifier, we have got forward bias diode. And I think that anti-log amplifier should have reverse bias diode, reverse bias diode, something like this. Okay. Since the inverting input is at virtual ground, inverting input, okay, here is a virtual ground, because we have got inverting input, Vin is going in inverting input, and we can, and non-inverting input is grounded, so we can say that here is virtual ground, and this potential and this potential are same. Okay. Since the inverting input is at virtual ground, the output is at minus Vf when the input is positive. Minus Vf. Okay, minus Vf. Since Vf is logarithmic, so the V out. Oh, when we saw the characteristic, the volt ampere characteristic of this diode, there was EF, as I remember from electronics course. It was E reversed biased ln, what was it? Yeah, in power. Yeah, that was the formula. And after that, we have got difference between, and this is logarithm, right? And this the diode characteristic causes that it is a logarithmic amplifier. Okay, as you remember in integrator, the transient processes caused the integrator, because the capacitor charges and discharges with something like this. No, it has got nothing common with this, so let's continue with this. When output is positive, since Vf is okay, minus Vf, the output is limited to a maximum value of approximately minus 0.7 volts, because it's the diode logarithmic characteristic is restricted to voltages below 0.7 volts. Also, the input must be positive when the diode is connected in the direction shown in figure. To handle negative inputs, you must turn the diode around. Input must be positive. So, we have got voltage drop on this diode 0.7 volts, and way out will be minus 0.7 volts, because again we are using inverting op-amp, inverting case. Inverting case. Basic log amplifier using a diode as a feedback element. Okay. Non-inverting input is grounded, and we have what here? A resistor, and we have what diode in the working. It has to be positive. Okay. It has to be positive. An analysis of circuit in as follows beginning with the fact that Vout is minus Vf. Yeah, it's right. And Ef is En because there is no current at the inverting input. No current at the inverting. Yeah, it's there is zero potential, and its input impedance is very high, and so there is no current. As you know, the current chooses the easiest, simplest way. For example, when you have here 1 ohm resistor with parallel of, for example, with 1 mega ohm resistor, the most current will come here, and the very low current will come here, because the voltages has to be same. Voltage has to be same. Minus Vf is, what's minus Vf? Oh, Vf is this diode formula, and Vf was this thing. Its Kt over Q is constant. V out is minus 0 V in over ER AR1. V out, okay. Input must be positive. If it's negative, it won't face. Determine the output voltage for the log amplifier in the figure E. I reverse biased is 50 nanoamps. Okay. IR, it's okay, this current, right? How can I determine that? The input voltage and the resistor value are given in the figure. Okay. V out we can count. That's it. Okay. Over Q, Ln, V in, IR, R1. Okay. How much is left? Converters. Why? let's continue. If I finish in 10 minutes, we will here. Long amplifier with a BGT, the base emitter junction of the people junction. Same type of logarithmic characteristics as diode, because diode has got only one p-n junction. For example, this P and this is N, and this transistor here has 3 PNP. For example, 3 layers of the semiconductor material, and it can use only 2 of it and act as a diode, because the base is grounded. So we have got something like this: NPN, NPN, because this arrow is going to N, from P to N, and the base is grounded, and we have got something like this. We use these parts. Yeah, that's right. A log amplifier with a BGT connected in the common base form in the feedback loop is shown in figure. Notice that V output is minus V base emitter voltage. Base emitter voltage, because this is inverting and this voltage is here. The analysis for the circuit is the same as for the diode log amplifier, except that VB replaces VF. Yes, that's where diode was. EC replaces EF, and EBO replaces ER. Okay. The anti-logarithm of the number is the result obtained when the base is raised to a power equal to logarithm of the number. To get the anti-logarithm, you must take the exponential of the logarithm. Okay. Anti-logarithm is formed by connecting a transistor diode in the input element as shown. Wait a minute. I thought that here the diode would be reverse bias, but they took diode here. Wait a minute. Yeah. That's right. This book is right and I'm wrong. Okay. V out is minus RFEC. Yes, that's right. The characteristic equation of the p-n junction diode is IC. The current here is same as here, because we have got virtual ground again. This V out is R, and this comes here, and it gets V out gets this. this Vout is whole. As you can see, V in is V base emitter. Base emitter, okay. V out. V in. V out is minus RFBO. Yeah. V out. Okay. This is anti-logarithmic formula. Oh, this is very important and interesting thing, signal compression with logarithmic amplifiers. In certain applications, a signal may be too large in magnitude for a particular system to handle. The term dynamic range is often used to describe a range of voltages contained in signal. In these cases, the signal voltage must be scaled down by a process called signal compression so that it can be properly handled by the system. If a linear circuit is used to scale a signal down in amplitude, the lower voltages are reduced by the same percentages as the higher voltages. Linear signal compression often results in lower voltages becoming obscured by noise and difficult accurately discriminate as illustrated in figure. Okay, when we have got some signal, there is some noise too, and noise have got actually sometimes high frequency and maybe sometimes high amplitude, and our good signal is something like this here. And when we make linear signal compression, the both parts of the signal gets compressed and the good signal gets destroyed. It shrinks very high. To overcome this problem, range can be connected with logarithmic response and B. Okay, we can compress only high amplitudes. High voltage are reduced by greater percentage. Nice.